Okay, everyone, so today we're going to talk about work and the work energy theorem. So we learned last week, it says this week, but we learned last week that energy cannot be created or destroyed. It only changes form. So that was the definition of conservation of energy. Now, if that's the definition of conservation of energy, then how exactly does an object gain or lose energy? That's the question that we have for today. Now, work is the only way energy can be transferred from one object to another. So, the definition of work is energy that's transformed to or from an object by means of a force acting on the object. If we have positive work done on an object, the energy transferred to the object it's going to be transferred to the object. And then if we have negative work, then the energy is transferred from the object. And I'll give you examples of both so you can see what I mean by this. So here's kind of a picture of what's going on. So a force acts upon an object to cause a displacement of the object, all right? And that's really important, is that if there's no displacement here, then no work is actually done on an object, okay? So the force must cause the displacement. Now, work can be done to change either the kinetic energy or the potential energy of an object. So if we are changing the kinetic energy, something like making a car speed up or slow down, that's going to involve work because we have a change in kinetic energy here. Remember, if we're speeding up, our kinetic energy is increasing. If we're slowing down, our kinetic energy is decreasing. So if we have an increase in kinetic energy or we're speeding up, then a positive net work is done on the object. And then if we're decreasing in kinetic energy, so slowing down, negative net work is done on the object. Notice how I'm saying net work here for kinetic energy, and we'll talk a little bit about this later. But we have multiple forces acting on this object. So the driver is putting his foot on the gas pedal, therefore the chemical energy in the gas is going to have reactions and then cause a force to force that car forward. We also have frictional forces within the car that are kind of taking away some of that energy. So in order to speed up, we have to have a positive net work. So the force from the gas pedal has to be greater than the force from the friction inside the machine and all that stuff. All right, so it's a positive net work or a negative net work done on the object. If we have no change in energy, that means no net work is done on the object. This doesn't mean that no work in general is done. It just means the net work is going to be zero. All right, like I said, we can also do work on an object in order to change the potential energy of the object. So if we change the object's location or orientation, that's also going to involve work. Now here, we know that this weightlifter is increasing the potential energy of the barbell because he is lifting it up, right? He's increasing the height. So he's changing that object's location and therefore changing the potential energy. So positive work is done by this weightlifter when he lifts the barbell over his head because he's increasing the potential energy. If he lowered that barbell down, he would then be doing negative work on the object because he would be decreasing the potential energy of the object. All right, so the work equation, like I said before, in order to do work, a force must cause a displacement. So the equation for work is equal to FD cosine theta. Now, F is the force doing the work. D here is the displacement. Now, I know that we've been using delta X and delta Y for displacement. I don't know why they like to use D for this equation. You'll see it whenever the work equation is written. For the most part, they use D for displacement. I don't know why they like to do that, but for some reason they use D here. Remember, this is the same thing as delta X, as just a displacement. And then we have cosine of theta, where theta is the angle between the force vector and the displacement vector. This is really important where that angle is, and I will explain what I mean by that in multiple examples that we're going to do today. Now, the unit for work is just the same as the unit for energy. It's a joule. And remember, that is a Newton times a meter, or remember, Newton is a kilogram times meters per second squared. So it's kilogram times meters per second squared times meter also. All right, so first example, suppose that you apply a 60 Newton horizontal force to a 32 kilogram package, which pushes it 4 meters across a mailroom floor. How much work do you do on the package? So for most of these examples, I'm going to draw a little picture. So here's my package is 32 kilograms for the mass. We're applying a 60 Newton horizontal force. So the force is horizontal, it's 60 newtons, and then we're pushing that package 4 meters across the mailroom floor. So we're going to push that package a displacement of 4 meters. All right, so our work equation is force times displacement times the cosine of theta. Now I know the force is 60 newtons. I know that the displacement is 4 meters. And then I need to think about this theta here. Now, if I look at this force, we can see that the force is going to the right and the displacement is going to the right. So remember that angle in cosine theta, it's the angle between the force vector and the displacement vector. So here, the angle between these two things, because they're parallel to one another and they're going in the same direction, that angle is 0. All right, so it's going to be cosine of 0, which is just 1. So we get work is equal to 60 newtons times 4 meters times the cosine of 0. We end up getting that the work done is a positive 240 joules. So since the work done is positive, that means that we are increasing the kinetic energy of the object. So that object would be speeding up. All right, example number 2, suppose that once you stop applying the force on the package, it slides to a stop in 0.5 meters due to a 6 Newton force of friction. How much work is done on the box by the force of friction? So this is the same situation as before, but now we stop pushing and then it's going to slide to a stop. Now this means that the box is still moving to the right like I had it before, but now we have a force of friction that's slowing it to a stop. So again, let's draw that box. I know that it's moving to the right, okay, but the force of friction is making it slide to a stop. So which direction would the force of friction be? It would be to the left. So that force of friction is 6 newtons, and then I know it's going to slide to a stop in 0.5 meters. So we're still going to the right, but now that displacement is 0.5 meters. So again, let's write down our work equation. So we get work is equal to force times displacement times the cosine of theta. Now in this example, force is going to be 6 newtons, that's the force of friction. Displacement is 0.5 meters now, but what is this theta? It's not 0 anymore. All right, remember theta is the angle between the force vector and the displacement vector. So if I look at my drawing here, force vector is going to the left, displacement vector is going to the right. So the angle between the two is actually 180 degrees. All right, 180 degrees. So now we are going to plug in that 180 degrees for our theta. We get 6 newtons times 0.5 meters times the cosine of 180. Cosine of 180 is actually -1. So we end up getting the work done is -3 joules, which makes sense because if we have friction involved here, it's slowing to a stop, right? We're losing kinetic energy, and therefore negative work has to be done on that package. All right, example number 3. We have this figure here and we can see that there's a force there, there's a displacement, and there's an angle, and we want to know how much work does the man do on the cart. So our equation, work is equal to force times displacement times the cosine of theta. Now in this case here, we can see that the force is 50 newtons, all right, the displacement is 30 meters, and then again, remember this cosine of theta, that's the angle between the force vector and the displacement vector. So we have the force vector up at an angle here, and the displacement vector is here. So that means that that angle has to be that 30-degree angle because it's between the force vector and the displacement vector. So we get work is equal to 50 newtons times 30 meters times the cosine of 30 Plugging all those numbers into our calculator, we get about 1,299 joules. That's pretty easy. All right, example number 4, we have if the man in the figure is holding the briefcase with a force of 50 newtons upwards and traveling to the right a distance of 10 meters, how much work is done on the briefcase by the force? So here, they give us force, they give us displacement, they even give us that angle right here, 90 degrees. So let's plug our numbers into our equation. So work is equal to 50 newtons for our force times the displacement of 10 meters times the cosine of 90. Now, what is the cosine of 90? Well, you might have already seen this or thought about it in your head. Now, cosine of 90 is 0. So here we get the work done by that force is 0 joules. Now, remember, in order to have work done, that force must cause the displacement. This force right here that's directly upward from his arm on the briefcase, this is not causing this displacement here. So therefore, that force does no work on this briefcase in order to move it that 10 meters, which is why the work done is 0 joules. Anytime you have this angle of 90 degrees, cosine of 90 is 0. So you're going to have no work done on the object by that force. All right, one more example, and then we'll talk about something else. So we have a weightlifter performing a clean and jerk with 300 kilograms. If he lifted the barbell a total distance of 2.5 meters, how much work did he do during the lift? Now, for something like this, we need to draw a free body diagram because they don't give us a force, right? Do you see that? They give us a mass and they give us a displacement, but they don't give us a force. So here's my barbell. Remember, free body diagrams. It's a beautiful barbell right there I have. We have the weightlifter's force upwards, and we have the force of gravity on the barbell downwards, or the barbell's weight. So we know force of gravity is equal to mass times acceleration of gravity. They give us the mass of the barbell is 300 kilograms. So, and I know not G, our acceleration of gravity, is 9.8 meters per second squared. So I plug those numbers in order to find the weight of the barbell. So I get 300 kilograms times 9.8 meters per second squared. We get 2,940 newtons for that. Now, with problems like this, we kind of assume that the force that the weightlifter puts on the barbell upwards in order to lift it over his head, we assume that that's just going to be equal to the weight of that barbell. We kind of say that, oh, it's going to happen at a constant velocity, meaning forces are balanced. So here, my applied force upwards is going to be 2,940 newtons in order for that weightlifter to get that barbell up and over his head. So now we have a force, we have a displacement of 2.5 meters, and then we know that that barbell, the displacement is upwards as well. So the angle between the applied force and the displacement is 0. So we get work is equal to force times displacement times the cosine of theta. So we get 2,940 newtons times 2.5 meters times the cosine of 0, and we get that the work done by the weightlifter is 7,350 joules. Okay, so work energy theorem. So like we talked about before, in order to increase or decrease the kinetic energy of an object, work must be done on the object. If an object's at rest, work is required to get it moving. If an object is moving, work is required to bring it to rest. So the change in kinetic energy is equal to the net work done on the system. And we talked about this already, but now we're actually going to have an equation for this. So the net work done on the object will be equal to the change in kinetic energy. Now, I'm just going to derive this equation right here. The net work done is equal to change in kinetic energy. I'll show you where it comes from. You don't have to like even write this down if you don't want to. But it is interesting. You guys know all these equations, you've learned them all before, so you can see where this equation actually comes from. So this is one of your kinematics equations. We have final velocity squared equals initial velocity squared plus 2 times acceleration times delta x. Now, in order to derive this equation here, what I'm going to do now is use Newton's second law. So force is equal to mass times acceleration. I'm going to solve this equation for acceleration. So acceleration is force divided by mass, and then I'm going to take this and plug it in for acceleration in the first equation. All right, so we end up getting final velocity squared equals initial velocity squared plus 2 times force times displacement over mass, because I plugged force over mass in for acceleration. Now, I'm going to multiply everything by mass here in order to get rid of it on the denominator in that last term. And then we're also going to subtract mass times initial velocity squared from both sides. And look, this is starting to look kind of familiar, right? Look at this, mv squared. Now, what we're going to do next is divide everything by 2 in order to get rid of this 2 on this side. And we end up getting 1/2 mv final squared minus 1/2 mv initial squared. So you can see that this is final kinetic energy minus initial kinetic energy equals force times displacement, which is just work. So we get final kinetic energy minus initial kinetic energy equals force times displacement. So again, this is our change in kinetic energy. And then this right here is the work done on the object. So that's where this equation comes from. This is the work kinetic energy theorem. Now, again, this is the same equation. So we have the net work done on the object equals the final kinetic energy minus initial kinetic energy. So if we have positive work done, we're going to increase the kinetic energy. If we have negative work done, we're going to decrease the kinetic energy, because we can see that if final kinetic energy is greater than initial kinetic energy, this whole thing and therefore this will be positive. If this is lower than the initial kinetic energy, then we'll have a negative work done. So here, note that the speed or velocity is squared here, okay? So if the speed of an object is doubled, the kinetic energy is quadrupled, and that's really important for certain things in like conceptual questions for these problems. We'll talk about, how much work is required to double the speed and things like that. So it has a exponential relationship. So we have it takes 4 times as much work to double the speed. And then an object moving twice as fast takes 4 times as much work to stop, because again, the speed is squared here. So if we double this, we're quadrupling the amount of work that it takes to double the speed. Now let's talk about stopping distance too. It's the same idea as what I was just talking about. So we have the work energy theorem applies to decreasing speed as well. The more kinetic energy something has, the more work is required to stop it. So again, here's our equation. So the net work is equal to our final kinetic energy minus the initial kinetic energy. If we're stopping something, that means that final velocity is 0. So what I did here is just plug in 0 for final velocity. So that whole term becomes 0. And then we're plugging in force times displacement for work done. Now, if I slam on the brakes in the car, it's the force of friction that's bringing that car to a stop. So I plugged in force of friction times displacement. So now what we're doing is we're looking at this equation right here. So for cars of the same mass, the frictional force that stops the car when you slam on the brakes is nearly the same. And then the stopping distance we can see then is proportional to velocity squared. Our d is proportional to initial velocity squared. So we can see here that if I double that velocity, right, I'm doubling this, but when you double something, you have to also square that 2. So we have 2 times initial velocity, you square the 2 and you square initial velocity. So therefore, we are going to quadruple this displacement or the distance that it takes to stop that object. So if we double 45 kilometers per hour, we're quadrupling the displacement that it takes to stop. If we again double 90 kilometers per hour, we have to quadruple this displacement that it takes to stop. So we go from 40 meters of stopping distance to 160 meters of stopping distance. So you can see when you double that velocity, you're quadrupling the work required to stop that car. And since the force is nearly the same, what you're doing is you're quadrupling the stopping distance. All right, so let's do one more before we stop. And this is number 8 on your homework. So I'm helping you out with this one here. So we have a 2.5 gram bullet traveling at 350 meters per second, hits a tree and slows uniformly to a stop while penetrating a distance of 12 centimeters into the tree's trunk. What force was exerted on the bullet in bringing it to rest? And if the bullet was going twice as fast and the tree exerted the same amount of force, how far would the bullet burrow into the tree before it came to a stop? So I've already written our givens down here. I forgot to do the animation, so there you go. We have a mass of the bullet is 2.5 grams. Now remember, this is really important that we don't use grams in physics. So we have to convert to kilograms. So that's 0.0025 kilograms. Our initial velocity of the bullet is 350 meters per second, and then it says it hits a tree and slows uniformly to a stop. So that means final velocity is 0. And then it says it penetrates a distance of 12 centimeters into the tree's trunk. So again, just like grams, we don't use centimeters in physics. So we have to change this 12 centimeters to meters. So I get 0.12 meters. And then we want to know what force was exerted on the bullet, bringing it to rest. So we're looking for force. Now here we know that we have a displacement. We want to know force. So force times displacement, that's work done on the object. And then we can see that we are changing kinetic energy, right? We have kinetic energy initially, and then that bullet comes to a stop. So therefore, we have 0 final kinetic energy. So we're going to use the work kinetic energy theorem. We have our net work done on that bullet from the tree is equal to 1/2 m mass times velocity final squared, our final kinetic energy, minus initial kinetic energy. So I'm just going to plug in force times displacement for our net work done, because the force of the tree times that distance that the bullet burrows into the tree. And then we know that we come to a stop here. So the final velocity is going to be 0. So this whole term cancels out to 0. And we end up getting force times displacement equals negative 1/2 mass times initial velocity squared. So now what we can do is we can plug in our numbers. We want to know force, so we just leave it as F. Displacement is 0.12 meters. Mass is 0.0025 kilograms, and then initial velocity is 350 meters per second. So plugging in our numbers here, we get force times 0.12 meters equals negative 1/2 times the mass, 0.0025 kilograms, times velocity squared, initial velocity, 350 meters per second squared. So I just plugged this whole thing into my calculator first. So on the right-hand side, we get a negative 153.125, and the unit for this is joules. And then we're going to divide both sides by 0.12 meters in order to solve for force. So divide both sides by 0.12, and we get a force of, that should be negative 1,276.04 newtons. Now, the reason this should be negative here is because if we're saying that the bullet is going in the positive direction, this force of the tree would be opposite the motion of the bullet in order to slow it down to a stop, right? It's like a resistive force. So that should be a negative force. So that's our answer. Now it says, the second part here, it says if the bullet was traveling twice as fast and the tree exerted the same amount of force, how far would the bullet burrow into the tree before it came to a stop? Now, if we look at this equation right here, we can see that if it was traveling twice as fast, I would be doubling this initial velocity. All right, if I double initial velocity, really what I'm doing here to this whole term is I'm quadrupling that, because I would have to square that, right? So we are doubling this initial velocity, but that whole term then gets squared. So we're quadrupling the amount of work that's done. And since force is the same, that means displacement then is being quadrupled. So displacement is proportional to velocity squared. All right. So since we're doubling velocity, we're quadrupling displacement, which means that that bullet would burrow 12 centimeters times 4. So what is that? 48 centimeters into the tree before it came to a stop. All right. So I hope this helped. This again, we just did number 8 on your homework, so therefore you try it again by yourself, maybe. But at least we did 1 on your homework. And feel free to email me if you guys have questions. Please show up to office hours on Wednesday if you have questions, and I will talk to you guys soon.